the problem.
I like that. Yeah, that is a good explanation. What else can you tell me? That's very good. What else do we know about the periodic table? Yeah, is that a hint?
It includes all the atoms and bonds.
Yeah, very good. Very good. So, what I want to propose to you, and again, how many of you did I teach grade 9 science?
No.
I think some of you. And how many of you I don't think I taught anyone here grade 10 science, did I? All right. So, different teachers teach things differently, and that's a good thing. It is very good for you to be exposed to different ways of looking at things. But I want to teach you kind of my approach to the table. Because I'll tell you what I'm not a big believer in. I'm never going to ask you to memorize things from it. I think that I actually think that's really weird. What is the point of having a reference if we're then like, great, now memorize it because I'm not going to let you have it? The whole point of the periodic table is that it is a graphic organizer. It's a reference. It's a place where that information is put that's designed for you to be able to use as a resource. So I'm never going to make you memorize it. I think that's weird. I don't get that. I'm not saying it's wrong. Somebody made you memorize it. Good, that's great. But it's not me. Not for me. Not my philosophy. But I want you to be able to read it. I want you to be able to look at it and really understand why it's laid out the way it is, because it has a tremendous amount of information in it that you can get very quickly just by looking. So, let's take a look. Recall the basic structure of an atom. Of course, who can tell me the basic structure of an atom? Our simple, Bohr-Rutherford model of the atom tells us.
Protons and neutrons in the center, and then electrons orbiting.
Very good. We have protons and neutrons in the center, and we have electrons orbiting, and they orbit in orbitals, right? We imagine these orbits. Really quickly, does anyone remember how many electrons we say fit in that first energy level, fit in that first orbital?
2.
2 is correct. Good. Thank you. How many fit in that second shell?
8.
Thank you. You got this. That's good. I like it. All right. So we fit 8. And normally we kind of draw these at like the compass points, north, south, east, and west in pairs. Sometimes that's not how it's done, but that's how I will do it typically. So there we go. That is the typical model of the atom. So protons and neutrons in the nucleus. And of course, the protons and neutrons we know are the heavy part of an atom. So the mass of the atom is found centrally in the nucleus. Of course, most of the atom is just
Empty space.
Empty space. But then in the orbits, in that empty space, we find the electrons in orbits. And they are in specific defined orbits. And we said, remind me, the first shell holds then
2, then 8.
Then 8. Does anyone know what comes next?
16, I believe?
I think it's 18.
It's 18? Yeah, we'll talk about it. Okay, we'll talk about it. If you take the grade 12 university chem, you will actually learn a little bit, just a little bit, of the math of why this is so. It's not random. It's not actually just arbitrary. It's also not just made up. It's not just an organizational thing that we tell you to kind of help sort it out. There's a real physical reason why this is how it works. For this course, you're just going to have to take it on faith. You're just going to have to believe me when I tell you that the lowest energy orbital, the first orbital shell, can only hold 2 electrons. The next can hold 8, the one after that 8, the one after that 18. You're just going to have to believe me. Why wouldn't you? I'm a believable looking guy, aren't I? Tough, but believable. So that's the basic nature of an atom. Now here's the thing you're going to learn. Chemistry is really the study of what happens when one atom bumps into another atom, and then they stick together. And then, when those 2 atoms are stuck together, bump into another atom, or maybe into another group of atoms, and what happens then? That's what chemistry is. It's just things bumping into each other and sticking to each other. Does that make sense? It's just a highly choreographed dating game. You know, right now we're a couple. Oh, now we're a couple. Boom, this and that. And then you get your real stable things, and they're like, we're together, we're married, we're this, we're stuck together.
There's a lot of polygamy and...
Well, yeah, we'll get to that. Anyway, so having said that, I was once studying for an anatomy exam, a second-year anatomy exam, and my grandfather, who was very Italian, had a friend named Mario, who was a doctor, also very Italian. and I was studying for this anatomy exam, and he decided he would take it upon me to quiz me at Christmas dinner. So Dr. Mario was quizzing me, and I was getting stressed out. I was just trying to eat my pasta, and he was going, you know, like, where's the greater trochanter of the femur located? And I was like, I really just want to eat this meal. But he was a great guy. So at one point, he was quizzing me, and I was doing all right, and he said, what's the first cranial nerve? You know what your cranium is, right? Your head?
7.
So you have nerves in your cranium, and he said, what's the first cranial nerve? And I couldn't get it. He said, what's the first cranial nerve? And I said, I don't know. And he said, and then he said, and this is weird, he said, if I took this plate and hit you right in the face with it, what's the first thing I'd hit? And the answer, of course, is the first thing it would hit is my nose. And the first cranial nose is the olfactory nerve. Sorry, the first cranial nerve is the olfactory nerve. But that's how Mario, this tough old Italian guy, decided to communicate that to me. If I hit you in the face with this plate, what's the first thing I'd hit? Sounds like you had a real bedside manner, eh? Nice doctor. But having said that, same idea. If this atom goes and bumps into another atom, what's actually doing the bumping? What part of this atom is going to interact with a part of the other atom when they collide?
The electrons.
Ah, beautiful. Say it nice and loud.
The electron.
The electrons. Chemistry is the study of electrons because when one atom bumps into another atom, the nucleuses are not colliding except in very extreme reactions. What do we call the kind of reaction where one nucleus is colliding with another nucleus? Nice and loud.
Nuclear reaction.
Nuclear reactions. That's outside of the realm of normal chemistry. In normal chemistry, we're not having nuclear interactions. Nuclear interactions are chaotic, and they're very high energy. You have to get things going very, very fast and very aggressive to make that happen. In normal chemistry, nuclei don't interact with one another. What interacts with one another is the electrons. In fact, not only is it just electrons that interact, but let me ask you this. Am I going to react with that electron right there? What do you think? This electron here, I want to react with that one. Is that likely? When I bounce into this, which appears to be a neon? Argon? I can't even think. What's the second noble gas? Whatever. When I bump into this, I think so too. I should really know that. I'm the teacher. When I bump into this, am I going to interact with that electron?
No.
Why not?
Because it's on the inner shell.
Yeah, that's right. Makes sense, right? You know, if this is about colliding and reacting, it's that outer shell that's going to behave. So here's where we go with this. Chemical reactions happen between valence electrons. And there's a word we're going to talk about. What's the valence of an atom? Because that's a language we're going to use a lot. We're going to say the valence shell, or sometimes just the valence, or valence electrons. What's that word mean? You just told me, when I bump into this, what electrons am I going to interact with? Yeah, beautiful. The ones in the outer shell. Which means that for all intents and purposes, what is going to define an atom's chemical behavior, its chemical properties, the way it reacts, is what that outer shell looks like. Does that make sense? If two atoms have the same outer shell, they're going to behave similarly. And this is how the periodic table is grouped. We put all of the atoms that have one outer electron in a column because they all behave similarly. That's your sodium, your lithium, your francium, your rubidium. They all have one electron in that outer shell, and they all behave similarly. In their case, because they just have one electron in their outer shell, they want to get rid of it. Those are highly reactive. But does that make sense? They're almost interchangeable. Even though they're totally different atoms, because they have the same outer shell of electrons, their chemistry is basically the same, because when you bump into any one of them, what you're bumping into is an outer shell that has just one electron in it. Does that make sense? It's the noble gases on the other side of the periodic table, which for you guys would be over here. On the other side of the periodic table, they all have full outer shells. They all behave basically chemically the same. They're all inert. They don't react. Because when you bump into an atom, you bump into the outer shell. So if you know what the outer shell looks like, you know what its basic chemistry is going to be like. Does that make sense? So the periodic table sorts atoms by outer shells. It's a good system. System that makes sense. The crazy thing about it is the periodic table is actually designed before we knew about electrons and before we knew about outer shells. The arrangement was already there based on how these things behaved. And the neat thing is, once we discovered the electron and how electrons are arranged, it lined up with how we had already grouped all the atoms. Isn't that kind of cool? So I've put a periodic table here. It's just missing a little bit of information. What's it missing?
The elements.
Yeah, all the stuff.
Just a little bit.
All the stuff, but that's okay. Because this is how I want you to think of the table right now. Don't worry about the individual elements. I want you to think about what this tells us about an atom. And really, the location on the periodic table tells us two things. So we said, how many electrons fit in the first shell?
2.
Hey, what do we notice about the first row? How many elements are in it?
2.
Oh, interesting.
2.
How many electrons did we say fit in the second shell?
8.
Oh, hey, how many electrons are, how many elements are in the second row of the table?
8.
2, 3, 4, 5, 6, 7, 8.
Huh.
Stop!
What's happening?
You have done
Everything
this.
fell apart.
Cortana, leave me alone. Okay, there we go. In the next shell, we said it fits 8. And oh, look at the table. 1, 2, 3, 4, 5, 6, 7, 8. Then we said the next shell holds how many electrons? 18. Hey, what do we notice about the table? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, the table is designed to tell you about the electron shells. That's its arrangement. So if I count, so say we're talking about this element right here. All right? That one. There's no names on here. Do I know what that element is? I could look it up. I could get a real table, but I don't actually care right now. I'm talking about that element. What do I know about it? How many shells does it have?
8.
How many shells? You're right. You're right. It's the shell it's in holds 8. Very good. But how many shells does it have? 2 full shells, right? It's past the first row, so its first shell is full. It's past the second row, so its second shell is full. It's in the third row, so it has a third shell. How many electrons are in its third shell?
4.
And how'd you know that?
It's the 4th on the
It's the
row.
4th on there. Look. 1, 2, 3, 4. We just drew a Bohr-Rutherford diagram of that element, and we don't even know what element it is. We didn't quite draw a Bohr-Rutherford diagram, because what's the one thing we don't know?
What it is. The
Yeah, and what does that matter? The neutrons. But the thing we know is that the neutron number can actually
Different.
change. It can be variable, right? There's different isotopes. So we have the major information right there. Does that make sense? I look at that, and I count down, and I say it's in the third row. That means there's 3 shells. I count over and say 1, 2, 3, 4. That means in that third shell, there's 4 electrons. What about the previous shells? They're going to be
8.
8, and the one before that?
2.
Because all the shells below the outer one are always
8 and 2.
Yeah, true, totally true. They're always full. Good. Does that make sense? So if I wanted to draw, oh, I don't know, this guy right here. Do I know what element that is? No idea. But hey, can you tell me about it? What can you tell me about the Bohr-Rutherford diagram for that? If I was going to draw it right here, I'm going, okay, there's that. I don't know how many. I could count to get the number of protons, but I don't care. Yeah, what do you know?
It's 4 shells.
Okay, good. Pause. So it's going to have 1, 2, 3. Wow. Make sure you do a better job than I'm doing. It's going to have 4 shells. How does he know that?
It's on the 4th row.
It's It's on the fourth row. Does that make sense? And then the first 3 shells are going to be full. I could go 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Okay. Yeah, there we go. And then what about the shell it's in? How do I know about that?
It'll have 5.
Yep.
We'll have 5 in.
Good. Yeah, you both got it. How'd you know that? You just super geniuses?
Because it's not the 5th one.
The 5th one in. 1, 2, 3, 4, 5. And boom! I have no idea what this element is, but I just drew a Bohr-Rutherford diagram of it. I drew the world's worst Bohr-Rutherford diagram. If you drew a Bohr-Rutherford diagram that looked like that, I would give you 0. But it doesn't change the fact that without knowing what element I'm looking at, I just drew a Bohr-Rutherford diagram. Questions about that? Or does that feel pretty good? Have you been shown that before? I hope so. I hope you've seen that, because that's why we have a periodic table. That's why we don't just have a list of elements. This is why it's designed that way, because it visually gives us information instantly. It's a really useful tool. So use it as a tool. If you think of the periodic table as a helpful thing, it becomes quite helpful. Don't think of it as your enemy, make it your friend. So, what does the row tell us? Row number is just number of shells. And they're all full except the last one. You can put that in your own words, all right? Those are the words that make sense to me, but I don't want it to make sense to me. I already know this. I have a degree in it. I want to make sure it makes sense to you. So how do you explain to yourself that I know that magnesium must have how many shells? How many shells does magnesium have?
3.
How many? What do you think?
3.
3. How do you know it had 3?
Fifth and third.
Because it's in the 3rd row. So don't copy my words. My words aren't important. What's important is that you know that when you're figuring out how many shells something has, you just look what row it's in. Use the words that make sense of that to you, your words. Draw a little picture, sketch it. I want you to get in that habit. Taking a note isn't about writing exactly what I've written on the board. It's about understanding what I'm talking about. And if it takes me explaining it 5 different ways, if it takes asking, Kylie, please explain this to me, then ask Kylie, please explain this to me. Like, do what you got to do. How many times a week do I go across and say, Kelford, please explain this to me? I don't understand. A lot. And every once in a while he does that for me, but I think he's just doing it out of pity. So he'll be like, hey, Joe, how do you log on to the computers? And I'm like, oh, like this. And he's like, oh, yeah, thanks. That was good. I didn't know how to do that. And I feel good all day. I'm like, I'm so helpful.
Who's Mr. Ionization?
That's right. All right. Now, what does counting over tell us? So magnesium, we said it has 3 shells. The first shell is going to be
Full.
full. And how many electrons does it hold?
2.
2. And here's the great thing. If you ever forget, if I ever said, how many shells fit in the 3rd electron shell? You'd be like, oh, man, I don't know. Do you have to have it memorized?
No.
You're always going to have a periodic table. You go like, oh, first shell holds 2. Next shell holds 1, 2, 3, 4, 5, 6, 7, 8. So you know what I mean? It's all there. It's all visual. So magnesium, its first shell is full. It holds 2 electrons. What about magnesium's second shell?
Full.
It's full. How many electrons in it?
8.
Awesome. What about magnesium's 3rd shell?
2.
Beautiful. How did she know that? Is she just a super genius? Just way smarter than me? Is that it? How did she know it holds 2 in its last shell?
There's the second one over.
Because it's the second one over. And counting over tells us how many electrons are in the outer shell. By the way, is everyone comfortable with me doing that for electrons, E negative? You know what I mean by that? Cool. Awesome. By the way, I want to make one little note. Does everyone know that these 2 rows are actually way longer than they look? To make the table not be way too wide, because see how the table keeps getting wider, right? Like the first one's only 2, next one's 8, 8, then 18. These 2 rows actually have this in there. Can you see that? These 2 rows actually belong in these rows. So these aren't actually below on the table. If you look at the numbers, that's 56, and then that's 72. How do we get from 56 to 72? That's 57, 58, 59, 60, so on. Do you see that? Did you know that?
Yeah, I told this was very nice.
Well, look at me. Well, if you didn't know that, make sure you know that. So how many electrons actually fit in this shell, in the 1, 2, 3, 4, 5, in the 6th shell? How many electrons fit? Well, it would actually be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Am I ever going to make you draw a Bohr-Rutherford diagram of radon?
Yes.
No. I have no interest in counting the electrons in a Bohr-Rutherford diagram that has 32 electrons in its outer shell to see if you got it right. I'm not going to do that. But that's how many electrons fit in that shell. Does that make sense? So it actually goes 2, 8, 8, 18, 18, 32, 32, and that actually covers every known atom. That covers all of them. That gets us there. Because once you get up past that, things are pretty much immediately unstable. They just fly apart. They're too big. Too big to be sustained. Questions about that? So, reading the table. Reading the table, real important, because then I really quickly, if I give you chlorine, you look and you say, okay, 3 shells, first shell full, second shell full, third shell almost full, missing just 1. Instant. Does that make sense? If I say oxygen, you look instantly and say, cool, 2 shells. First shell full, second shell not quite full. It's 2 away from full. And that piece of being able to look at an element and say, I know what its electrons look like, that's chemistry. Chemistry is about electrons. Does that make sense? All right. We're going to talk about a couple other trends on the periodic table. Real quick like. Can I move on? Like we're good? We got this? All right. Oh, I just typed something. Ki. Oh, Ki. That's getting very close to my computer trying to tell me something. Like that time it said Fu. It's like, hey. Hey, computer. Never mind. Okay. Do you know, I once had a student, I taught advanced functions, and at the end of every semester, though not in recent years, because in COVID times I'd be too sad to read what people have to say about my class, because I think it would be like, I hated every second of this and that makes me sad. But usually I always give like an end of a course survey, tell me about it, what'd you like, what didn't, what should I change, what should I keep the same, all that. And I taught advanced functions one year, and one kid just, the only comment on his entire survey was, you put the advanced FU in advanced functions, and I wasn't quite sure what to make of that. Anyway. Like I don't even know what that means, but it hurt my feelings. Okay, the other thing I want to do is when we look at the table, there's some things we should be able to say roughly about an atom really quickly. Does that make sense? Just real quick, looking at the table. If I look here, I should be able to say a few things about that atom. We can already say how many shells, right? We can already say how many electrons in that outer shell. Awesome. Another thing I want to be able to say, again, not with a number, all right? Not like 2.6 times 10 to the negative 23 meter. Nothing like that. But a real quick and dirty kind of sense of how big an atom is. So really quickly, if we go back and look at the periodic table right here, all right, there it is. We're looking at it. What would be an example on here of an atom you imagine is probably a really little atom, a small one?
1.
Yeah, I mean, and obviously the one that should jump right out at us is hydrogen, right? I mean, it's only 1 proton, 1 electron. That's really little, right? What would jump out at us as probably being a really big atom? If you had to guess.
180.
Yeah.
UU.
Yeah, as you get near the bottom, they're going to get big, right? And why do you think that? Because you're totally right, of course. When we get near the bottom, why are they bigger?
Bigger numbers.
Bigger numbers, and bigger number, bigger atom, that's reasonable. Specifically, what's there more of? More protons and neutrons. Now, they're in the nucleus anyway, and we say an atom's mostly empty space. So does it matter if there's more protons and neutrons? I don't know. But what makes out the outer part of the atom? The the electrons. And as we get down here, if this thing has 118 protons, it must also have 118 electrons. And those all have a negative charge. And if they all have a negative charge, do they want to be close to each other? Do like charges say like, hey, let's hang out? No, like charges do what?
Stab each other in the knees.
They repel, right? So like, probably if we have 118 electrons, they're going to be like spread out, right? So our instinct is probably to think smallest and biggest. Does that seem like a good guess? Logical, right? Fewest electrons, most electrons. Now, of course, the reason I'm drawing this all out is that that is
True.
not true. It's wrong, but it's close. It's good thinking, but we're going to talk about this. The trend is actually a little bit surprising, and I wonder if we can figure it out. First of all, do we agree that as we keep adding shells, these things must get bigger? Right? Like, surely, if we add a second shell, it's got to get bigger, right? And a third shell, bigger still. Fourth shell, bigger still. Is that, nobody's contesting that? We're cool with that? All right, because that is true. I'm not toying with you there. So, each new shell increases the radius of atoms so moving down the periodic table, atoms get bigger. Okay, that seems pretty logical, right? We all cool with that? Okay. Now, having said that, I'll go back up, so don't worry. If you actually look at this graph, though, what happens as we go across the periodic table? Like, if we compare lithium and neon, they both have two shells, but which one is bigger? Lithium. And if we compare cesium and radon, which one is bigger?
First one.
Yeah. So, but this is weird because this has more electrons, this has more electrons than that, right? As we go across the table, we get more electrons. Why are they shrinking? Why do they get smaller going across the table? And I mean, obviously I'm going to tell you, so if you don't know, don't stress about it. But does anyone have any ideas what they think it might be?
Would it be less neutrons?
Neutrons can vary, but as a rule, more protons also means more neutrons. Good thinking, though. I like that, thinking about the particles, for sure.
The shells are further apart in, was it cesium? Or whatever the element.
Mm-hmm.
Bottom left.
Yeah. So why would the shells have more space between them in cesium than they do in radon? Because you're right, they must be, right? The shells are compacting in as the atom gets bigger. Why would that be?
Because I'm going to say because there's more full ones.
Same number of full shells, right? Because all the shells above are full.
There's less loose.
Good thinking. Let's go back to the model of the atom. What's in the middle of the atom?
Nucleus.
The nucleus. And what's in the nucleus? Protons and neutrons. What charge do the protons have? Sorry? And the electrons are in the orbit, right? Yeah. What charge do the protons have? Positive. What charge do the electrons in orbit have? Negative. Okay, now, we said like charges repel, but opposite charges attract. This is the thing. My wife, she's a very positive person. Me, unrelentingly negative. Instant attraction. That's just how it works. It's not actually how it works. If you're a very positive person, you probably want to avoid people like me who are just miserable and negative all the time. But my wife sucked her in. And now I own half the house. What's she going to do? Trapped. So anyway.
I'll sue you.
I'm kidding. We love each other. It's a joke. Anyway. So the protons attract the electrons because they have opposite charges. Well, if you think about it, go look at this periodic table. As we get bigger, what has more protons in the nucleus? Cesium or radon? See, every time we go over, we get another proton. And every time we get another proton, the nucleus is a little more attractive to those electrons. Does that make sense? So barium's got a little more positive charge in the center, so the electrons pull a little closer. Tellurium, a little bit more, pulls closer. Lead, a little bit more still, so the electrons pull closer. Bismuth, a little bit more. Does that make sense? And they keep pulling in because every time you add more positive charges to the nucleus, the electrons are more attracted to the nucleus, and those shells move closer to the nucleus. So as we move across the periodic table, even though we have more electrons, they move closer to the central mass. That's the trend. Does that make sense? All right, let's write that so we know it. As we move across the table, more positive protons in the nucleus pull the electrons in, and the atoms get smaller. Cool. And I usually draw this. I usually show that as we go down the periodic table, they get bigger. And as we go across the periodic table, actually, we'll just go this way. They're bigger on this side. Does that make sense? I'm going to come back to this, so don't stress. But just to look here, what is the largest element? Should we assume, based on this? What is the biggest element on the periodic table?
87.
Sure, what is that? Does anyone know? FR?
Is that francium?
It is, good. Yeah, very good job, guys. Francium we would expect to be the biggest element because it's got the most shells, but of the ones in this shell with this many shells, it's got the fewest protons in the nucleus to pull them in. Does that make sense? So those shells can spread out way more than radium all the way up to unknown 118, which I think has a name now. What would we expect to be the smallest atom? The most tightly compacted atom on the entire table. What would we expect?
Helium?
Helium. Good. Because it's only got one shell, but it's got 2 protons instead of just 1. So those electrons are really pulled in tight. Just 2, and there's twice as much force pulling them into the nucleus, so they're going to be even closer. To say nothing of the gravitational force, because helium also has 2 neutrons, and gravity also plays a factor here, but don't stress about that. Do we feel like we understand radius? Not too bad, right? So again, this is not a perfect hard and fast rule. You can look up the exact radiuses, but we want to get in the habit of just thinking. When I look at where something is on the table, I want to know stuff about it. Does that make sense? Now if I point to an element, you can tell me how many shells, you can tell me how many electrons in its valence, and you can tell me roughly if it's a big atom, a medium atom, or a small atom. Does that make sense? You can compare it to its neighbors. And looking at the table that way, it's not about reading the numbers on it. It's not about memorizing it. It's not about knowing any of that. It's about understanding the layout of the table and what it can tell us. All right, I'm going to give you a couple of minutes to write that if you need to write that. Ask me questions if you got them. That's what I get paid the big bucks for. Right, Kat?
Is dead.
Yeah.
I know something different.
Sorry?
I know something different.
Oh, sure. You bet. If you look, just turn auto save on. Oh, it doesn't want to. Okay, just and the nice thing is it's saving. Oh, one second. That's interesting. Let's just make sure. One things, because it should save this info. Why in goodness name? Just gonna fill that. Give me a second, okay? I'm gonna have to think about that. Please does. Yeah. Oh no. Can I take a look? I don't know. Sorry about that. Let's see if we just I'm going to go take a look at mine and see if I messed something up. Because goodness knows that happens. Sorry about that. Give me just a moment. Let's go check something here. That's odd, because I have it on my side, like I have it on both my computers, so it did distribute. Oh, good. Okay, sorry about that. Not sure why that would take so long. Okay. So, having talked about that, I want to talk about another trend, which is related to this one. We said that chemistry is all about, specifically, what part of the atom?
Electrons.
Good. Specifically, what types of electrons?
The outermost of the electrons.
The outermost ones. Good. Does that make sense? When you talk about chemistry, really, despite the atom being this big complicated thing, really, it's just interactions of those outer electrons. Does that make sense? Now, as it happens, we're going to review all this in later lessons, but you know this. What are the two basic ways in which those electrons interact? I'm an atom, I got some electrons. Nathan's an atom, he's got some electrons. We bump into each other. Basically, three things can happen. One, I'm happy with my electron setup, he's happy with his electron setup, we just bounce off. No change, right? Your noble gases do that. Helium bounces into argon, they're both just like, I'm good, I'm chill, I got a full shell, I'm happy. Argon's like, yeah, me too, they're good, and they just, boom, they just bounce off each other. Does that make sense? No interaction. That's a possibility. What else can happen? They can react. And when they react, what do the electrons actually do? What can that look like? Who remembers? Grade 9 science, grade 10 science. What actually happens to electrons when they bounce into each other?
One electron goes to the other atom and then the other.
Good. They can give and take. By the way, the universe is a violent place. It is! The universe is a violent place. A sodium atom bumps into a chlorine atom, and chlorine's just like, that's mine. I'm taking it. That's what happens. It's not this friendly interaction. It is a give and take environment where when they bounce into each other, the strong one takes from the weak one. It just happens. Electrons can be given and taken. What happens if they both want more electrons, but they're both pretty equally strong? See, like, look, I'm big and tough. I know it's intimidating, so listen. I have a bit of lunch money, Nathan has a bit of lunch money. I'm big, strong, and intimidating. Nathan and I have not found my wallet, but when I do, I will have some lunch money. So Nathan and I bump into each other in the hall. I'm just taking his lunch money, it's mine, Nathan. And he's gonna be like, whatever man, just don't hurt me. He's gonna give me his $3 and I'm gonna go buy a sandwich. I'm gonna add it to my $2, now I got $5, I go to the caf. Mr. Pouliot, I'd like a sandwich, please. He gives me my sandwich, I eat it, and I'm going to go find Nathan and eat it right in front of him. Exert my dominance, right? Because I'm tough, I get it, right? But let's say in a different world, Trush bumps into Nathan, and Trush is like, hey Nathan, give me your lunch money. Nathan's like, yeah, no. And Trush is like, well now what do I do? I've got $3, Nathan's got $2, what do we do? What do they do? If neither of them is willing to give up their lunch money, what could they do?
Put it together.
They could put it together. Maybe they say, hey, between us, we've got $5. They go down to the cafeteria, they give the $5, they get a sandwich, and then they go, let's enjoy this delicious sandwich together. I'm not doing that. I'm way too tough for that. But Trush, he's easily intimidated. He's cowed by people of equal stature. I understand it. Not everyone is a physically imposing individual such as myself. And he would just say, let's just share. Let's share.
Trush walked in.
I'd intimidate him with my toughness. What kind of a question is that? Trush fears. They don't fear me, except Bainbridge. I'm afraid of Bainbridge. I love Bainbridge. She's like the nicest person I know, but I wouldn't cross her. She's tough. I wish I were tough like she's tough. Anyway, I just talk about being tough. Bainbridge doesn't talk about being tough because she's actually tough. she's not just making it up like I am. Anyway, so those are the three basic things that can happen, right? Two atoms can bump into each other and say, we're good, we're cool. They go off. Two can bump into each other and there's a power disparity. One really wants electrons, one doesn't have much of a hold on its electrons. In that case, giving and taking happens. That's me and Nathan. Or they bump into each other, they both want electrons, but one is not more powerful than the other. They can't give and take. And in that case, they are forced to compromise. They're forced to share. We have names for those types of interactions. What do we call the kind of compound that happens when there's giving and taking?
Covalent, I believe. Yes.
That's the other one. That's the other one. What do we call it when it's give and take? I'm stealing. Ionic. I'm making you an ion. I'm taking from you. Covalent, if you think about co, if I co-parent with my wife, it means that we do it together. We are the co-owners of my house, right? Mr. Calford and I often collaborate, which means we laborate together. Laborate. Work. We work together. Language all comes together. I'm starting to think this English language might be onto something, right? So covalent. We know what the valence is. The valence is the outer electrons. A covalent compound is one where we share the electrons in our outer shell. A little bit of name there. Now, what determines if I'm going to say, don't even want electrons? Or if I say, I'm so hungry for electrons, I'm taking them. Or if I say, I'm hungry for electrons, but let's share. What makes that difference? What makes that difference? Well, let's look at our periodic table. We said lithium. Tell me about lithium. Tell me about it. What do we know about it? What do you know about lithium looking at this periodic table? How many shells? How many electrons in its outer shell? Is it big? Is it small? Tell me about it. Go. Cool. How many should there be if that were a full shell? Cool. By the way, is lithium big or small?
Small.
Well, it's a bit of both, isn't it? Let me ask you this. Bigger or smaller than hydrogen? Bigger than hydrogen. Bigger or smaller than cesium? Cool. Bigger or smaller than oxygen? Bigger. Yeah, good. Cool. So, lithium's got one electron. If it were going to crawl its way up to a full shell, how many electrons would it have to steal? 7 more. On the other hand, if somebody were to steal from it, how much would it lose before it was just stable and happy?
2.
Not even. How many electrons in its outer shell?
1, rather.
1. So, what do you think is more likely? Is it more likely that lithium is such a tough guy that he's going to go out there and steal 7 electrons? Or is it more likely that he's the kind of guy who's going to get like, sorry, it's my electron, dude?
Lithium is more likely to roll in.
Does that make sense? Listen, if I were lithium, I'd be like, I'm getting a full shell. I don't care if I need 7. Listen, if I'm cesium, I'm getting a full shell. I'm like 31 more electrons, I'm on it. Listen, there's 20 kids in this class. That's less than 2 from each. I can do that. But the reality is everything in the first column is just going to lose them. Does that make sense? Because it's a lot easier to lose 1 electron than it is to gain a bunch. Does that make sense? So we measure this with a trend called electronegativity. Electronegativity is how hungry for electrons an atom is. Its technical definition is the measure of the tendency of an atom to gain electrons. That's true. That's its technical definition. But what that really means is how electron hungry is an atom. How much does it want it? And as a rule, it is basically the opposite of the size trend. Because if you think about it, everything that makes an atom small makes an atom unlikely to give up that electron. Does that make sense? If you think about it, like, who's it going to be easier to steal an electron from? Rubidium or hydrogen? Yeah, why? It's bigger, and so its outer electrons are pretty far away from the nucleus. Does that make sense? Right? Like, rubidium's outer electron is way far away from its nucleus. So there's less pull on those electrons, easier to snatch away. Does that make sense? Whereas hydrogen, still relatively easy because it's only got one electron in its outer shell. Hydrogen's reactive. But even still, quiet.
Ding, ding.
I don't know what this means, but my watch currently thinks I'm exercising. This is the sad state of the physical affair of my life where it's like, well, this is more exercise than I normally guess. I guess we'll call this thing where he's talking animatedly a workout. Oh, that's so humiliating. Anyway. Hydrogen, those electrons, still easy to steal because there's only one in the outer shell, but it's a lot closer to the nucleus. It's a lot closer to that positive charge. Going to be a little trickier. Does that make sense? So basically, here's the nice thing. Electronegativity is basically the opposite of size. Does that make sense? A big atom will tend to have a low electronegativity, and a small atom will tend to have a large electronegativity. Make sense? The only exception is the noble gases, which essentially have no electronegativity. Why do they have no electronegativity at all? They're the one place it breaks down.
They already have a full valence shell.
They have a full shell. Do they want more electrons? Are they going to give up their electrons? No, they just are basically stable. But as a rule, electronegativity follows the exact opposite trend of radius. Oh, my pen is acting up. I gotta change the battery in it. And so we'll show this. Now, the first thing we said is, what column in the periodic table has essentially no electronegativity? What column on the periodic table has no desire for more electrons?
Noble gases.
Yeah, so we can take these and we can say these are basically not electronegative at all. I'm going to just cross them out. But other than that, which side of the periodic table is more electron hungry? Which side is trying to get rid of its electrons? Which side is trying to get more? Well, we said these ones only have a couple, so they are going to tend to lose them, right? Whereas this side is almost full. So they're really hungry for more because if you are chlorine, you are one electron away from a full shell. Does that make sense? So electronegativity increases as we move across. We have high electronegativity on the right, low electronegativity on the left. But it also increases moving up the periodic table. The small atoms at the top of the periodic table are more highly electronegative than the big ones at the bottom. Questions about that? Cool. We're going to talk about electronegativity a lot. That's going to be a term we use a lot. Because, again, chemistry is all about the movement of electrons. Chemistry is all about what electrons do. So knowing how electron hungry an atom is a really useful piece of information. Very useful information. Questions about that? By the way, you can get the specific number for electronegativity on the periodic table. A bigger periodic table, electronegativity is one of the numbers on it. If you just Google, if you go to ptable.org, which is, I think, the best periodic table out there, you can click and say, right now, show me all the electronegativities. And It just has the symbol and the electronegativities on them. You can get the specific number, but just glancing at the table, you should have a sense of where the most electronegative and the least. So looking back at our periodic table, what is the most electron-hungry element on the periodic table? What wants electrons more than anything else? Don't answer yet. Take a minute and look. I want everyone to kind of think of what their answer is. The most electron-hungry element on the periodic table should be what? What do you think? Don't worry if you're wrong. I'm wrong. I don't know if you know this. I'm wrong all the time. Yeah.
Hydrogen?
Good thinking, because it's up there, so we like that. But we said the other thing is, and you know what? Like hydrogen could even be close to the answer. There's actually one that's a little bit more, though. But that's very good thinking, because it's right at the top, right? But as it happens, the trend in the other direction is a little bit stronger. But that's a great thought. But even more than hydrogen? What do you think, Thibaut?
I would have thought USS, the 117.
Ah, that's good thinking, because it's way to the right, and we know as we go to the right, they get more hungry. But remember we said that the smaller they are, the closer that outer shell is to the nucleus, and so the pull's even stronger. So between the two of you, you've got it figured out, because we want to be up, but we also want to be to the right of the table. Meaning?
Fluorine.
Fluorine. Fluorine's the guy. It is the most electronegative. It's the most electron-hungry thing. We use it for that reason in organic chemistry a lot. If we want something that's just going to be an electron taker no matter what, you can bubble fluorine gas or something, and it will take electrons. It is electron-hungry. What is the least electron-hungry? What on here is not, compared to everything else, it's not trying to get electrons, it is giving them for sure. This thing is going to lose electrons, not gain them. Yep, very good, exactly right. That's called francium, and it's the exact opposite. This thing only has one electron in its outer shell, and that outer shell is way out in friggin' Narnia, all right? It is like so many shells away. It's 1, 2, 3, 4, 5, 6, 7 shells away from the nucleus. One lonely little electron, 7 shells away from the nucleus. Imagine you took, I don't know, hypothetically, your missing wallet and put it like 70 feet from your house, just sitting there. Is somebody going to be nervous about taking your wallet?
No.
No, it's practically on the other side of the street. Someone's just going to snag it, right? Whereas if you're hydrogen and you put that wallet like on your front step, someone might still take it, but are they going to be as quick to take it?
No.
No, they're going to think, well, if this guy has one of those like camera doorbell thingies, I don't. Or, you know, like what if he comes out and like beats me up? And then he's like, was that Orlando's house? Better not.
Something
Anyway,
tells me
that guy's
this is
tough. Sorry?
I'm going to steal your wallet.
That's if you
Well, first you have to find it. Listen, I would love for you to steal my wallet. Because if you stole my wallet, it would mean you had found it. Because listen, I don't think my wallet's been stolen. I think that I went, oh, I'm going to put my wallet down. Ooh, I'll put it this place. I won't forget I put it there. And I think it is sitting in that place right now. And I think 50 years from now when I'm dead and gone, someone's going to buy my house and be like, oh, there's a wallet behind this book. Wonder why that's there. Sorry?
Isn't your driver's license?
Everything's in my wallet. I have digital copies of all those things, so you always photograph your ID. But I've never lost my wallet. I'm very ashamed. Like, I'm stressing out about this because I'm like 38 years old. I've never had to replace like a credit card or a piece of ID or anything. I've just always had it.
You locked your credit card in case?
No, I just keep checking it every day. Nobody's used it except me. My son used it the other day to buy a skateboard. So I was like, did you steal my wallet? He's like, no, I just have the number written down. And I was like, we got to talk about this. I'm not sure how I feel about that. Right? That's a different discussion. Anyway, I was like,
Written down?
don't use
Why
my...
not just memorize it?
I have it memorized. Do you have your social insurance number memorized?
No.
No.
You should
but I
memorize your
have my
social
wallet.
insurance number. Once you get a credit card, you should memorize your credit card number. You should know these things. Come on.
I have my Wi-Fi password memorized, and it's just a shit ton of random numbers.
EF1CD 5C3. That's the Wi-Fi password. of the Virgin
7019165.
Mobile Network. There you go. See, I like that. Okay. So anyway, we're going to talk about 2 more trends. 2 more things to know about, which are related. They're really the same thing. Electronegativity tells you how electron hungry something is, right? That tells you how much they want to get electrons. That make sense? Well, but getting electrons isn't the only thing that happens. What else can happen? You can get electrons, but you can also lose. So ionization energy is related. This is the amount of energy required. Oh, this is lagging. It's like struggling. The amount of energy required to remove an electron from an atom. And you can actually have first ionization energy, which is the amount of energy required to remove the, help me out here. The first ionization energy is the amount of energy required to remove the first electron from an atom. You can have second ionization energy, which is the amount of energy required to take a second electron, and so on and so forth. Does that make sense? So the amount of energy required to remove an electron from an atom. In other words, if I have an atom and I add, I'm going to use a different color here. That's what I'm going to do. Try and stop me. If I have an atom and I add energy, I can then get that electron free. And now, what do we call an atom that has lost or gained an electron? Once it has a charge, does anyone remember what we call it? Now I have an ion. And will this particular ion have a positive charge or a negative charge if I've taken an electron from it?
Positive.
Very good. Does that make sense? So ionization energy is the amount of energy required to remove an electron. You don't have to stress about it. This is not one we talk about as much. That's why it's just kind of a little other thing. But you're going to hear me use that language a couple times through the course, ionization energy. Just know that when I talk about ionization energy, I'm talking about how much energy it takes to take away. It's related to electronegativity, because if something is really electron hungry, are you going to get electrons away from it easily? No. So if it's got a high electronegativity, it's also going to have a high ionization energy. Does that make sense? If I'm really electron hungry, not only am I trying to get your electrons, but I'm also not really interested in giving up mine. Does that make sense? Okay. And then the last one is really not important. We almost never talk about it, but I want to mention it for completeness sake, because note, to take an electron away, what do I have to put in? Energy. Does that make sense? If I want to take your electron, I got to put energy in. It's like if I want to take your lunch money, Ivan, I got to put the work in. First of all that work of all those years of intense exercise that my phone tells me about, like talking in the front of a class to build up this physique, then I got to be like, hey, Ivan, that's a nice $3 bill you've got in your wallet there. It'd be a shame if something happened to it. Hand it over, bud. I'm going to put it in my wallet. And he'd be like, where is your wallet? And I'd be like, shoot, I don't know. And then while I was scratching my head wondering where my wallet was, Ivan would just run off and he'd be gone. He'd go to the cafeteria and buy a sandwich. But if I'm going to take an electron, I have to put the energy in. But I want you to think the natural, obvious side of that. If you have to put energy in to take an electron away, what's the opposite of that? What must happen when I get an electron?
You also gain energy.
Lose energy?
Let's not think about gain or lose. Let's think about put energy in. Energy goes into the atom versus energy comes out. Energy is released. Does that make sense? So we have to put energy into an atom to make it lose an electron. But if when the other atom gains an electron, it actually releases energy. It releases it typically in the form of, when you think of a reaction releasing energy, what's the most common kind of energy a reaction releases? You know this. You do a chemical reaction, and you better be careful because it might be
Explosive.
It could be explosive energy. It could be movement. But more often, things get hot. Does that make sense? So losing electrons actually requires putting energy in. And you see this because you think sometimes to make a reaction happen, we have to heat it up. We have to put energy into the reaction, right? But then sometimes other types of reactions, specifically ones where electrons are being gained, when atoms gain electrons, energy is released, and we call that energy the electron affinity energy. Again, you don't have to be super stressed about these two. This is not the important part of the lesson. The important part of the lesson is those trends up above. But how would I write that? If I said I have an atom, and if I'm having it gain an electron, it's going to be an atom plus an electron, good. And what's that going to give us? Well, what does an atom become once it has a charge? Good. And in this case, what will that ion's charge be if it's gained an electron? Negative. And we said when an atom gains an electron, it will release energy. So I should say plus energy. Now, the fact of the matter is every reaction involves gaining electrons and losing electrons. That's not quite true. But most reactions involve both of these things happening simultaneously. So there's energy being released and gained all at once. Both things are happening. Does that make sense? As a general rule, it takes energy to take an electron away from something, and you get energy, you release energy when you get an electron. It goes into a lower energy, more stable place. So these trends on the periodic table, all very important, but let me tell you the most important things. This note goes in descending order of importance, all right? In other words, this stuff we did at the beginning, reading the table, that's the most important thing. Make sure you get that. Make sure that I can point at an atom and you can tell me how many shells, how many electrons in the outer shell. Boom, boom. Does that make sense? That's real important. Then, next most important is radius and electronegativity. That's really important too. We care about those. They're important. We want to know about them. And then the last stuff, ionization energy and electron affinity, that's kind of interesting, nice to know, not the big deal. Does that make sense? Cool. Yeah.
Yesterday we were talking about how to